Up next is Dr. Dk Panda, professor and university, distinguished scholar of computer science and engineering at The Ohio State University. Dr. Panda has published over 500 papers in the area of high-end computing and networking. The MVAPICH2 libraries designed and developed by his research group are currently being used by more than 3,100 organizations worldwide in 89 countries. More than 815,000 downloads of this software have taken place from the project site. The RDMA packages for Apache Spark, Apache Hadoop, and Memcached, together with OSU HIBD benchmarks from this group, are also publicly available. Dr. Panda's talk will start with an overview of challenges being faced by the AI community to achieve high-performance deep learning and machine learning on modern HPC systems with both scale-up and scale-out strategies. Dr. Panda will then focus on a range of solutions being carried out in his group to address those challenges. Welcome, Dr. Panda. You may begin.
Okay. Thanks, Brian, for the kind introduction. Good morning, everybody in Australia, in that part of the world. And otherwise, it is what? Good day, good afternoon, good evening for people in the other parts of the world. Thanks for joining this talk. It was a pleasure last year for me to present actually in person in the Australia conference. But this time we are doing it online, and hopefully next year we'll be able to have it in person. So today I'll be mostly focusing on high-performance deep learning and machine learning on modern HPC systems. How do we go about it? How do we extract the best performance and scalability for the emerging fields of the deep learning and machine learning? So as you can see, like we are in an exciting world. This is like the data from the top 500. As you can see, like we have reached the 415 petaflops, the Fugaku system. We started crossing like the 100 petaflop in 2017. Just in 3 years, we are there up to 415. And of course, the next goal is to reach the exaflop. And people have been discussing, and we'll see, might be the next year, we'll have one of the countries will be trying to deliver the exaflop system. Now, in that context, traditionally we have focused on HPC, but nowadays, at many places, you must be hearing about all the AI, deep learning, and machine learning. So as you can see here, AI is a very big field. It has been there. The concepts were there since 1950s. People started also like a machine learning principles, where you try to do feature extraction plus classification based on a set of inputs. So those concepts started from 1980s. Like some of the examples are like k-means, random forest, linear regression, nearest neighbor. So these are the algorithms which are very much used in the data mining field, quite a lot. And then gradually, people started moving into the deep learning, where you, instead of like trying to do feature extractions by a manual intervention and doing the classification, can the machine actually combine these two, the feature extraction and classification together? So this is where the deep learning is a subset of machine learning that uses the deep neural networks and based on the learning data representations. And we see a lot of examples like the different kinds of CNN, convolutional neural networks, recurrent neural networks, and also hybrid networks. Now, some of you might be familiar, or if not, the deep learning has broadly two phases. First, provided a lot of data is available, we want to actually train or come up with a model. And this is no different than, let's say, our a regular child learns the thing. Over the years, as you know, like a boy or a girl from the childhood keeps on learning. Just to give a very simple example, sometimes you might have seen a child doesn't know what fire means. So if there is a fire, the child actually goes and puts the hand. And then after you put your hands 2 or 3 times, the child knows that there is a fire, and then you don't have to touch it. So that is the kind of the training happens for us, all of us throughout the life. Same examples happens in driving, in a day-to-day life, we keep on getting trained. And then once we get trained, then of course the situation comes with the inference or the deployment. So that means if just like the example I indicated, like the child's example, if 2 or 3 times the child knows that it is detecting the fire and fire is not good, next time you show a fire, the child will not actually put the hand. So that is kind of an inference. The same thing with like a driving example. If you make some accidents, you learn from that, and then the next time when you are driving it well. So these are the kind of the broad two phases. Whatever we do as human beings, we are trying to take that kind of concepts into the computer. And especially this training is a computer and communication intensive process. And in the previous slide, as I showed, like in early 2010, prior to that, those concepts were there, but nobody were able to really compute or take care of the computation with a feasible time phase. So these used to take some months. But then, currently there have been, as the technology has evolved, now people are trying to push it to take it to days and weeks, or from the weeks to days, even sometimes to the hours. So that is where, like, we are trying to focus on faster training, and that is the biggest thing what we would like to know. And the faster training can be achieved using newer and faster hardware, like on a single node, if you have a single GPU or a collection of GPUs or some set of cores, you can do the training up to a certain extent, but there is a limit. So this is where the need for the parallel and distributed training comes. Like, can we use more number of GPUs or more number of nodes? Like the previous talk, Dr. Smith indicated, like the new system has 760 GPUs. Can you actually try to take care of all the 760 GPUs, trying to take care of a deep learning training and trying to do it in the best possible time? So while the deep learning is going on, of course, the other fields are coming up, especially in the data science. And this is where, like, a newer kind of a distributed computing framework called DAS is getting momentum. So it scales actually Python applications from laptops to high-end systems. You can build a task graph, and that can be executed lazily on parallel hardware. And it natively extends a lot of data processing libraries like NumPy, Pandas, etc. And in this context of DAS, also the NVIDIA has introduced this RAPIDS framework, which is a GPU-based data science ecosystem. It aims to achieve hide the low-level complexity of the CUDA framework, and there are a lot of components around there. So there also the same kind of challenge is coming, like how do you do DAS distributed? So that means instead of running it on a single node with a one GPU or few GPUs, can we actually try to run it on a large number of GPUs so that we can actually try to reduce the execution time of these applications. So then the machine learning is coming, like, again in a similar manner. The traditional ML algorithms, as I showed earlier, like a k-means, nearest neighbor, those kind of algorithms, again, the similar challenges are existing. Now, how we can actually hide the complexity of the CUDA programming, and we can scale out using the Dask ecosystem. And instead of like running on a single GPU, can we actually do within the node, like a single node but multiple GPUs? But the bigger challenges is this MNMG, which is multi-node, multi-GPUs. So I'll try to address these three things, the DL aspects, the Dask for data science, and also the QML, and trying to see how to accelerate these on the modern system. Now, if you put all these things together, so these are the broad two challenges. In the directions, we'll see one is the scale up. That means, which is intra-node communication. That means within a node, if I have like 2 GPUs or up to 8 GPUs, sometimes some of the latest servers have 16 GPUs, how I can scale with more number of GPUs. Or if I have more number of cores, like if you think of like the latest AMD platform, we have like a 2 sockets, dual sockets. If the ROM platform, you can go up to 128 cores. A single node, you have 128 core CPUs. Can I just, even using the CPU itself, the CPU-based training, can I do it scale to up to 128 cores? But then there is a limit here. So this is where like some of the components, the QDNN, MKLDNNs, they are trying to heavily optimize the libraries so that you can get good scale up. But then the question comes to scale out. If I want to go outside of the node and I want to scale to many more GPUs, and we need to have support for distributed and parallel execution. And this is where actually I'll show it in the next few slides. If some of you remember, the TensorFlow started with this gRPC, Google RPC. Some people tried to scale with Hadoop. Now there is a lot of focus on Spark. NVIDIA has the Nickel 2 library. But what I'll be focusing in this talk is actually you can try to resolve or solve all these problems using the MPI itself. Because MPI is a message passing interface standard, has been running on HPC platforms for almost last 30 to 40 years. And all the large-scale systems use MPI libraries. So instead of going through all the different solutions, can we directly utilize MPI and then try to get the best scale up and scale out? And that's what exactly my research group has been focusing for the last several years. And then I'll be trying to share some of these latest results and developments here. So the broad challenge, I'll be trying to focus in this talk, how to exploit HPC for both deep learning and machine learning. So in a problem statement, I can indicate like how to efficiently scale up and scale out both the DL and ML frameworks and take advantage of the heterogeneous high-performance computing resources. That means the systems have both CPUs and GPUs, and how do we scale it? So in order to go into some of the solutions, now let's try to see how people are trying to design runtime and how that relates to the programming model. So that will give us some ideas on how we come up with this solution. So in any of these examples I indicated earlier, like for example, if you take HPC, most of the applications are written with MPI, or the next generation applications are coming with the PGAS, which is the Partition Global Address Space. Examples like UPEC or OpenSMEM. People are using CUDA, OpenMP within the node, OpenACC, Hadoop, Spark, or in the DL, we have the TensorFlow, PyTorch, or the data science, we have Dask, and then the machine learning, we have QML. So these are the kind of the programming models. As an user or a programmer, you try to describe your application using one of these programming models. But then when you are trying to run, I call it like a supply side, like these are the HPC systems, or in the previous talk, we heard about capabilities. That means modern day platforms, we have multi-core many core architectures, accelerators are coming, GPUs, not only the traditional NVIDIA GPUs, but AMD GPUs coming up, FPGAs, and then all different kinds of networking technologies. InfiniBand has been there, Ethernet has been there, the Rocky, Omnipath, EFA, and Slingshot. So all these are coming. So you can actually build an HPC system by putting these commodity components. But then when people are trying to write these applications, whether it is HPC or DL or ML, I call it like a demand side. So that means they want to get the best performance from this underlying system. And of course, they will be using these programming models through some middleware. But then the question is to extract that performance, we need to design this communication library on the runtime with the best performance and scalability. So that means it has to have the best point-to-point communication protocols, collective communication protocols, energy awareness, synchronization, RMA operations, IO file system, fault tolerance. So like this, the list keeps on going. So once I can have this kind of a very highly efficient communication library and runtime, then I can try to take the performance and capabilities from this underlying hardware and then try to deliver it to the application. So this is a layered approach. Sometimes there are some co-designing also gets done, like at the different layers. People try to make some changes here, make some changes here, make some changes here, and then trying to put it together to get this kind of performance, scalability, and resilience. So in this context, in my group, we have actually been working in this area almost for 20 years now. So this is the MHAPICH project. And this project we started almost the day one of InfiniBand. When InfiniBand, if some of you remember, it was announced in October 2000, almost very close to 20 years back. Prior to that, in my group, we were working on the MPI libraries for the prior generation systems like Mirinet, Quadrix. Those were the networks of that time. When InfiniBand came with all the features like RDMA, reliable connection, non-reliable datagram, we were the very first ones to jump in. And then we actually came up with the first open source MPI version. And we indicated this MHAPICH. It is a derivative of the MPICH project. And we also focused on, if some of you might not be remembering, when the initial InfiniBand started, it had a verse level API or called BHAPI. So that was the layer on which we put our stack. So that's how that word was coined, and it has remained like that for over the years. Okay. So we had the first open source version. We demonstrated Supercomputing 02. Almost now 17 years back. It was working that time. I remember it was hard to even run an MPI on a stable system with only 8 nodes. Okay. But now you see over the last 20 years, systems are like you are putting zeros next to it. 8,000 nodes, 4,000 nodes with InfiniBand are continuously running in a stable manner. And we have been there in the community to provide that kind of MPI library over the years. So we started with InfiniBand, but over the years, we have also gone into the other interconnects, the Omnipath, iWarp, Rocky, and very recently also we have MHAPICH running on the AWS with EFA. We support all the different platforms. GPUs, NVIDIA, and very soon AMD is also coming up. Last week, actually, we had an MHAPI user group meeting. Quite a lot of people all over the world attended. We showed some initial numbers with AMD GPUs. That is the new release which will be coming out. And we also started with MPI 1 20 years back, but over the years as MPI standard has been evolving, we also have been evolving with that, and we support the latest MPI 3.1 standard. So there are different versions of these libraries. I'll touch some of these in the next few slides, but as Brian introduced, currently this library is being used by more than 3,100 organizations in 89 countries. These are based on voluntary registrations. A lot of people download and don't identify themselves. That is okay with us. But just from our OSU website, now we have crossed almost 0.8 million downloads. And we are hoping like by the end of the year, actually we'll hit 1 million download. In addition to downloading from our site, our softwares are actually available in all other vendors and Linux distros like Red Hat, SUSE, OpenHPC, and SPAC. But it is not just the download count matters. Over the last 15 years, we have been working with this community to really scale, and now our library is empowering many of the top 500 clusters. So these are some of the clusters in the June 2020 ranking, the 4th, 8th, 12th, 18th, etc. We are actually a partner in the 8th rank TAC, Frontera system, Texas Advanced Computing Center. I am a co-PI of that project, and I'll actually show you some of the numbers. That is the largest CPU, pure CPU-based system running with InfiniBand HDR. So this is actually the architecture of the MHAPIS2 software family. As I indicated, we started with HPC 20 years back, but as the demand has been changing, we have also morphed it into to support DL and ML. That's what I'll be talking about here. So at the top level, we support MPI, PGAS, hybrid MPI models. Here below, we support all the networking technologies, multi-marker architectures, but these are the inside mechanisms in our communication runtime. And since we are from academia, our primary goal is actually to come up with newer solutions. And every time like a newer technology comes or a newer mechanism comes, we actually publish those papers. And in 6 to 9 months, we have the capabilities to take it to actually our production library. So we have in my group now almost 200 servers continuously running QA testing, performance regression, logic regression, all kinds of coverages. We do almost like every commit, we spend almost like 18,000 hours to try to make sure that the things are stable. And once we have a set of features and ready for the release, we actually run it also on a lot of remote clusters where we have access to, and then only we put it into the release. So you can actually download these and directly it runs on many of these large-scale systems. So this shows quickly like a release time and downloads. These are our major releases. As you can see, we are in a very upward ramp over the last many years, going very up and up when people are downloading and using our stack. So there are a lot of HPC components which I'll not be focusing here, but I'll be trying to focus more on the DL and ML applications. That is the focus of the talk. And in this context, I'll try to start with the MPI-driven deep learning. I'll try to focus both on CPU-based deep learning as well as GPU-based deep learning. And then I'll go and trying to see the newer problems, whatever are coming, like let's say the model sizes are increasing, GPU has some limit on the memory. So how do you handle out-of-code DNA training? And also traditionally people have used only data parallelism, and because of the out-of-code training, people cannot use data parallelism. So we have started moving to model parallelism and hybrid parallelism. And using that, I'll actually show you a very nice use case. We are working actually with a digital pathologist and how you can actually train pathology data, and we have given them some impressive speed up in the recent months. And then I'll be talking more on the DAS side and the QML side. I'll also be talking about a commercial support and products through a commercial spin-off in the recent years. So let's start with basics of TensorFlow. As many of you know, like the TensorFlow has been there in the community for many years, and especially when the distributed TensorFlow started, there was the Google had this gRPC. That is the Google RPC. So that means when you go outside of the node, how do you handle the communication? The communication was being handled with RPC. But as you know, RPC is not a heavy-weighted protocol, so you don't get very good performance. So in fact, in our group also, we have done some accelerated gRPC, like gRPC running over native InfiniBand. But over the years, that actually moved to this middle framework where people call like a gRPC plus X. So that means some communication you can go through gRPC, and some other communication you can take it through MPI layer or verbs layer. Even on the GPU system, you can take it through the GPU direct RDMA layer. And finally, in the last few years, the field has moved to saying no gRPC, and this is where most of the recent focuses have been there. And the Horobird is the stack from Uber, which actually allowed to integrate underlying libraries. Either it could be from the NVIDIA, like the Nickel library, or it can also be linked with any MPI library. And we have taken this path, the MPI path, and that's what we are trying to take and enable through Horobird so that you can actually run all different kinds of DL applications. So this is our actually the MPI-driven infrastructure. If you take a look at this Horobird, so there are two paths here. One is directly through Horobird, like Horobird supports TensorFlow, PyTorch, or NMXNet. So when you are trying to run these, we have actually linked. We have two versions of the library. I'll be talking that in the next few slides. We have the MHAPIS2 or MHAPIS2X for the CPU-based training, and MHAPIS2 GPU direct RDMA, which is very highly optimized for GPUs for the GPU-based training. And then recently PyTorch is actually taking a little bit of different approach. So now you can run PyTorch is gaining momentum compared to TensorFlow, and that can actually run. There is a torch distributed or even the deep speed, which is the Microsoft is trying to push. So what we have done the very similar things, both torch distributed and deep speed. We have actually linked to our MHAPIS2X and then MHAPIS2GDR. So through either of these approaches, now if you have a need, you are running actually TensorFlow or PyTorch or MXNet, you should be able to download our stack and directly run it using MPI and get very good performance. And that's what I'll be trying to talk. And more details are actually available. We have a project page called High Performance Deep Learning or HIDL. So if you download here, there is a very nice user guide. It actually tells you step by step how do you go and configure your system with the Horobird library or torch distributed or deep speed, download our libraries, how to put it together, and then you will be ready to run your application. So I'll try to show you some of the results, what you can get from using our libraries, and you can actually download and get similar kinds of results. So let me start with the CPU-based deep learning. So this is where we have the basic MHAPIS2 library. We also have an advanced library, which is called MHAPIS2X. It has some advanced MPI features. So here are some basic performance just to get the low-level MPI numbers. These are like the one-way latency. These are on x86 system over the years. We are trying to go down and down. Currently, we are around like a 1 microsecond node-to-node latency. And for large messages, the bandwidth matters. So here with the ConnectX 6 SDR actually gives the good performance. Then unidirectional bandwidth point of view, this is like clearly you can see what has happened over the years with the different kinds of networking technology. This is QDR, this is FDR, this is dual FDR, EDR, Omnipath, and then this is the SDR. So this is around like a 24.5 gigabytes per second. If you multiply by 8, it's actually 100 gigabits per second. And then the right-hand side is the bidirectional bandwidth. So here we come to, ideally it should be 50. We are coming very close to that, 48 gigabytes per second, or very close to 200 gigabytes per second. As I indicated earlier, we also support all different platforms, not only x86. These are some open power numbers. So here you can see we are comparing intra-socket. So this is the MHAPIS2X. MHAPIS2X actually has a lot of advanced designs. One of the advanced design is XPMEM support. Another is a cooperative protocol. So now you can see as the message sizes increases, we can deliver actually very good performance compared to in like the on open power from IBM, the Spectrum MPI. Bandwidth-wise, we are very similar, like the intra-socket and inter-socket bandwidth. Internode, we are comparable to Spectrum MPI. We are a little bit losing here. We are trying to optimize that, but otherwise, like this is over the InfiniBand EDR. So we are able to get even here, as you can see, like for the medium message sizes, we are able to give even better bandwidth. So if you are trying to run some of these DL applications, as many of you might be knowing, it uses heavily collective. So collective support, when you are trying to do a forward pass and a backward pass, then you take the SDDs and you try to do all reduce. So any library need to really optimize all reduce to get the very good performance and scalability. And that's what we have done. with this XPMEM, as I indicated, like our MRP2X has XPMEM support. So we have very optimized XPMEM-based all-reduced design. So as you can see here, this is across multiple different libraries. We can actually give you factor of 2x, 4x improvement, or even this is like a 48% or 2x, 3.3x performance improvement for the all-reduced. And these actually get translated to the overall performance benefit. So this is a paper we presented at IPDPS 2018, 2 years back. So you can see like a performance of CNTK. But the CNTK level, so this is the basic MRP2, this is the MRP2 with XPMEM, and then we are comparing that time with Intel MPI, and you can see at an application level, we can actually give you some 20% or 9% benefit. And recently we have taken that approach and actually used the TAC Frontera, as I was telling, this is the largest CPU-based system. So we are able to scale the TensorFlow, as you can see it, like we used up to 2,000 CPU nodes. So each node has up to 56 cores. So it's almost like 112,000 cores, and we are able to give very good performance and coming very close to the ideal one. And we are able to report a peak of like 260,000 images per second. And we are able to train ResNet 50 using 2K nodes in just 7 minutes. So you can see that even the GPUs give you a lot of good performance, CPUs are not falling behind. So you can actually, many times, people have added a lot of CPU nodes. So you should still be able to carry out like CPU-based deep learning. But the more focused, let me go into the GPU-based deep learning and machine learning, because that's what the community is focusing, and the absolute performance also you get better. And in this context, let me introduce the concept of CUDA-aware MPI. Many of you might have heard of it. If not, let me introduce it briefly. So most of the time, if you see like this is a node and this is a node, this is a GPU. So you try to take, typically most of the time people do a CUDA mem copy, then do an MPI send, and then you do an MPI receive. So it helps to write very good program, but performance is not good. So what we did, this was a 2010, we actually published a paper in the International Supercomputing Conference saying, can we hide all this complexity from the end users? So for example, if the user knows how to program or they send the data MPI send from a host memory, instead of host memory, if you just put the device buffer as sender and you tell which receive device buffer it has to go, then you can just do, user can just say MPI send, MPI receive, the user doesn't need to even know CUDA or doesn't need to write anything in CUDA, but the underlying MPI library can actually try to move the data as needed with a good performance, and that can lead to good productivity. So we introduced that concept. Since that time, we have actually worked very closely with all the NVIDIA features and trying to provide that in our library, and other MPI libraries are also following very similar trend. And if you take a look at this number, this is the latest number. See this number, 1.85 microsecond. You can actually move data, short messages, from GPU of one node to a GPU of another node, not on the same node, in using only 1.85 microsecond. And if you don't use this is the standard, like with a no GPU direct option, you get this kind of performance. So almost we can improve the latency, reduced by a factor of 10, and improve the bandwidth by a factor of 9 or 11. And that leads to very great performance at the application level. So that was on an x86 system. This is from actually Open Power, like the number 2 summit. And the lesson, a lot of this top Open Power system, it is actually using the GDR copy 2, and it has also NVLink. So as you can see here, internode with the GDR copy 2, we are able to, again, node to node, we are able to deliver the data using only 2.18 microseconds. And within the node, when the GPUs are connected with NVLink, we are able to come very close to saturate the NVLink bandwidth, which is actually 65 gigabytes per second. So based on those kind of point-to-point, then we have optimized the collectives heavily. And what we have done actually, we have actually kernel-based support to perform these collectives. And here we are I'm trying to show some numbers comparing our MBAPIS to GDR, comparing to Nickel 2. This is from NVIDIA. So you can see these are already used on a DGX2 machine. So you can see, like, since MPI library always tries to optimize for all message sizes, small, medium, large, we are able to actually give you performance benefit here compared to Nickel 2. This is with Nickel 2.6 almost 4.7x better, 2.5x better. And one can actually, if you have access to DGX2, you should be able to actually download our library and then actually run it there. You'll get this kind of performance benefit. This is on the Oak Ridge Summit, the number 2 system. We are able to run this up to 1500 GPUs. And then here again, use the same story. We can actually give you better latency, better bandwidth. And in fact, for large messages, which are typically the deep learning frameworks are using, as you can see the bandwidth, we are able to give far better bandwidth compared to the other MPI libraries and then now if you are trying to run, like in this case, TensorFlow, trying to run with that hoverboard infrastructure I indicated with our MRP to GDR. This is on a DGX2 node. You can see when compared to Nickel, which is a part of the DGX2 library, we can actually push the performance around 9% and also give better scaling efficiency. This is just with 16 GPUs. So then we actually ran distributed TensorFlow on the Oak Ridge Summit with 1500 GPUs. So here we use the ResNet 50, but we use the ImageNet 1K. So this has 1.2 million images, and as you can see, we are able to run and get very stable performance and scale it, while Nickel was not scaling beyond some number of GPUs. And here we are able to train the entire thing in only 4.5 minutes. So now you can see how an MPI library like our MRP to GDR can help you to get the best performance in the training. So those are the TensorFlow numbers. We have also tried like a PyTorch that is getting a lot of popularity these days. Similar things hold good. You can see like compared to the nickel-based solution, you can actually push your higher is better, images per second, you can deliver 30% higher. The PyTorch with hoverboard, again here we can show like another 15% overhead, and these are with the very latest Nickel 2.7. And we also tried that PyTorch with DSpeed, the framework I had shown in the right, directly linking you to the entire library. So here again, we can also compare to Nickel, we can give you like a 10% higher benefits. Then Torch distributed, similar kind of story. So we are actually enabling through our MRP to GDR, so that irrespective of whether you go through hoverboard or you go through PyTorch distributed or the DeepSpeed, you should be able to get good performance. And this is a comprehensive results. If you are trying to utilize PyTorch, this is trying to show ResNet 50, trying to scale on 256 voltage GPUs. As you can see, compared to any of this approach you take, we are able to give you almost like a 10,000 images per second faster than nickel-based. So that shows the capabilities of our stack to really help the end users. So those are the basic deep learning results. But now let me move into some advanced stuff. As many of you know, like let's say Volta has only like 16 gigabytes or 32 gigabytes. So then what happens, the model sizes are increasing, and how do you actually try to now run your things if it doesn't fit in the model? So that's what we call it like out-of-core training. And in fact, we had introduced we had taken a framework like Caffe, we had done some out-of-core Caffe, and trying to show this was presented at HPC 18, and trying to show how it can actually deliver you better performance, or even try to make it feasible. But recently then what we are trying to look, most of you are familiar with the data parallelism, and that's what is being used currently. But if your model is very large, you cannot even fit into within the machine, then how you can actually run it. So this is where the newer parallelisms are coming, like a model parallelism. So that means you divide the model itself over different machines. Like this is the layer 1 will go here, layer 2 or layer 3 will go here, layer 4 will go here. Then there is a spatial or channel parallelism also concept is coming. So using that concept, now you can generalize. So based on like a GPU or CPU, so here it shows like the amount of memory available, and these are like the input image sizes. So now you can see different boundaries like a ResNet 1K and 5K. Once you go, like let's say even if you take like a CPU Skylake with 190 gigabytes, if your image sizes are even larger than that, you cannot even fit it into the CPU memory. So this is the reason where you can only do it with model parallelism. And that's what is our focus. We recently published a paper at the ISC, and I'll show you some numbers. And this is what we have taken. This is, we call it HyperFlow. So it is a hybrid parallelism, and with a 512 Intel Skylake nodes, the TAC Frontera connected with SDR100, we took this ResNet 1001 again with variable batch sizes, and now you can see like from the 512 nodes, we are able to give you almost like a speed up of 481x. Okay? And with a very good scaling efficiency, like on a 256, we get 98%, and 512, we can get like a very close to 94%. So then these are the basic training. So now we are working actually with some of the end applications people. As many of you know, like the pathologist, traditionally, like they actually trying to see the slides. Like you go to a doctor, they take a sample, the pathologist actually looks at the things and trying to perform. You need a lot of expertise there. That also is becoming very expensive these days. And the question is, can machines or a deep learning help pathologists? So because in any hospital, you have so many thousands of slides from all over the years, can you actually utilize that and try to train so that when a new sample comes, it should be able to, computer should be able to tell you very narrowly saying, yeah, this could be the reason, or this could be, it will guide the pathologist to reduce the diagnostic time, making pathologists productive, and in the end, it can reduce the healthcare cost. So this is the paper which is coming out in the Supercomputing 20. It has been accepted to be presented. So these pathologists use very large image sizes, 100,000 pixels. It cannot fit into the single memory. So when the pathologists were training, they were actually doing very nice things. They were only like scaling, they were using only on one GPU. It was taking actually 32 hours for them. And this is not a practical way for them to train. So first what we tried to do is scale up. So we used up to 4 GPUs on a single node, and we reduced from 32 hours to 7.25 hours. Then we scaled to 128 GPUs, like 32 nodes. And now you can see 27 minutes. So we have almost like given them a speed up of like almost factor of 60. And now they're very happy, and they are actually trying to use this framework. And this is all with our MFS2 GDR library. This is running on the Lassen, on the Livermore system. So with this kind of performance, now it becomes very practical for the pathologist actually to go to a complex model and trying to train their application. So then let me move into these two other domains. I indicated like the DASK. So this DASK architecture, as I indicated, is trying to focus on data science. So currently, actually, there are support through TCP or through ECX, which is a consortium which is developing the communication stack. So recently, what we introduced, like we introduced this MPI for DASK. There is a newer communication layer, and we introduced that, took it to MPI for Pi, and linked it to the MFS2 GDR. So now you can see these are some of the performance comparing the UCX Pi and then MPI for DASK. So as you can see here, this is like we can give you like almost 6x better performance, like in a short messages, and also for large messages also we can give you significant benefit. And then in the throughput, we can give you like almost 4x better benefits here. So those are the low-level micro benchmarks. But now if you take some of the examples, like this is a sum of Q pi array and its transport, these are public benchmarks we are trying to use. So now you can see like IP over IB, we are just showing it as a reference, but the main comparison between the UCX and MPI for DASK, because both are running natively over InfiniBand. And compared to UCX, we can give you actually 3.47x benefits, 6.92x benefits here. This is a CUDF merge operation, similar kind of stories like a 3.11x better, 3.22x better. And this is also like the sum of QPi and transpose with 6 workers itself, we are able to give you like a 6.57x better benefits, and a CUDF merge operation, we are able to give you 3.74x benefits. So it again shows the strength of our MPI library to actually efficiently handle the communication so that it can benefit all the data science applications. Similar things also we are doing with the QML applications. These are the machine learning applications. So again, currently people have been using, this is the entire QML framework. People are going to the UCX and the Nickel library. So what we have done, that we have introduced our MFS2 GDR support, and with a new component here, MPI for Pi. And to that, actually, we can use all the optimization of the collectives we have done in the library, all reduce, recast, etc., and look at the numbers. So these are some numbers very recently we took. These are k-means, linear regression, nearest neighbors, truncated SPD. So the bars are trying to show the relative time, and this is the speed up curve. Compared to Nickel, we are now trying to see here almost like a 1.6, 1.6, 1.4, 1.4 kind of things. We are able to deliver you benefits. So those are the kind of, again, these are the last two, Dask and QML are not been released. Very soon you will be seeing releases from our website. So you should be able to actually download and then utilize it for your QML applications. All the other things, whatever I indicated, these you can do as of today. Just download our MLP library and run it with TensorFlow, PyTorch, distributed PyTorch, or DeepSpeed. All those solutions are currently available. So these are all from our research side. But since last few years, we also have a commercial spin-up because many people want like a commercialized solutions here. So we have this commercial spin-off is the SQL Solutions. Actually, this is also a sponsor of this event. So through this, if any of the end users or supercomputer centers or even integrators they want, we'll be able to provide the best possible solutions with all these kind of features. We can actually do very application-specific optimizations with a timed response. Currently, we are actually providing support to several national laboratories and international supercomputing centers. And not only the basic support is there, we are also an ISB member of the Open Power Consortium. And in fact, last year at the Open Power North America Summit, we introduced two packages, XScale HPC and XScale AI. In fact, in the September 15th, we have the 2020 Open Power Summit. We have a presentation there, and we'll be introducing some new additions, and I'm trying to show some previews here. So here, with the XScale HPC, so we have taken the MLP libraries, and we are actually adding value-added things there. And one of the things we have done now is the Mellanox has this new Bluefield NIC, and we are trying to actually offload MPI offloading capabilities to these ARM-based smart NICs. And in fact, just last week, there was a presentation from XScale Solutions, so please take a look at this, the slides, to get more insight. And on the DL side, we have this XScale AI product. So it is powered by not only MLP library, you get all this performance, but it has actually like a very new features we have added, integrated profiling and introspection support. Because many times when you are running currently in the DL frameworks, if you don't get the performance, you don't know where the performance you are losing. So this is it can actually go into a cross-stack performance analysis in a visual manner and help users to optimize their DL applications. And it is bundled together here. You can actually one-click deployment. It supports x86, OpenPower, InfiniBand, Rocky, and NVLink. So the broad idea here is that currently to understand and analyze DL performance, you need a lot of different tools, multiple different tools, and trying to analyze where you lost the performance. So we are trying to provide this a single comprehensive solution so that you can actually train, profile, monitor, and analyze. So this is actually the software architecture. So there are a lot of different components, and it is linked with Horoword and TensorFlow, PyTorch, and it can run on all these interconnects. But this is how you can get a lot of details. So this is actually trying to run, let's say, sample things. When you are running, it actually gives you a lot of information, like how many collectives are being called through Nickel or through MPI stack. You get command line output, you get JSON format output. You also get a good dashboard. So for example, you can see as your application was running, these are the kind of the already used messages were being used. You can say like there are some 65 million messages and the latency was very high. So then now you can go back and see what happened to your algorithm or what happened to your middleware. So through visual introspection, you should be able to optimize your entire deep learning thing. So again, we presented more details in the MLP user group meeting talk. Please feel to take a look. If some of you are interested, please send us a note here, and we'll be happy to provide a demo and a free trial, and you can actually try to utilize it on your system. So with this, let me conclude the presentation here. As I indicated, both DL and ML applications require high performance and scalability. And in order to deliver that kind of performance, we need to have high performance middleware design. And that's what I presented today, especially the MPI or the MLP driven solutions. Not only it can help you the basic DL and ML, I provided out-of-code training, hybrid parallelism, and also provided solutions for Dask and QML applications. And also indicated about this commercial support and value-added product with deep introspection capability. So even the field is growing, of course, the next generation like the AMD GPUs are coming, Amperes are coming, people are going into really larger models. So there are a lot of challenges. I think next few years, we need to, as a community, we need to actually solve these to achieve scalability and high performance for the distributed training. So with this, let me thank all our sponsors. What I'm trying to show is actually 20 years of work. And I'd like to salute to all my heroes, which are the past, current students and staff. So there's a long list. So every time I give a presentation, I want to provide credits to them. But not only that, I also need a lot of new people. We have a lot of exciting projects happening since this is being presented in Australia. I would like to indicate if some of you are interested in coming and joining my group and would like your names to be listed in the previous page, please feel free to contact me. So with this, I'd like to thank all of you again. If there are any quick questions, I'll be happy to answer. Otherwise, you can contact me at this email. Thank you.